Hey there, and welcome to another session of college algebra videos. This is section 3.2, polynomial functions and their graphs. We're going to cover a lot of the stuff in the textbook, but not everything. We'll talk about basics of polynomials, recognizing some of their characteristics, talking about end behavior, and then using factoring to find zeros for polynomials and identifying zeros and their multiplicities. We're also going to use that information to graph polynomial functions. You don't have to worry about the intermediate value theorem or the turning point stuff towards the end of the section. You don't have to worry about that. So this is what we're doing today. A reminder here, a polynomial function is a function that looks like this. F of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1, da 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 da, all the way to a constant. A sub 0 through a sub n are real numbers. Some of them might be 0, but the first one can't be. And then x is your variable, and n is a natural number, number greater than or equal to 1. And this is called a polynomial of degree n. So the degree of a polynomial is the highest power. Okay, that's the highest power. And the number in front of the x with the highest power is called the leading coefficient. And both of those are going to be important for what we do later. The degree and the highest power will tell you about your end behavior, which we'll talk about in a minute. All polynomial functions have two characteristics. They are smooth and continuous. Smooth means that they are curves without any sharp corners, and continuous means that you don't have any asymptotes or holes or breaks in your graph. Okay? So, end behavior. End behavior is what happens as x goes far off to the left and as x goes far off to the right. We always put arrows on the end of our graphs, if you remember that, to represent that it keeps going. So we're talking about the end behavior. That's kind of where would you put your arrows? Where do you keep going? Okay? And so your polynomial function may jump up and down a whole lot, but eventually off towards the end it either goes up or it goes down. In the beginning it either goes up or it goes down. Okay? And so there are really four types of possibilities for this. Your end behavior can be falling to the left and rising to the right, rising to the left and falling to the right, rising both directions or falling both directions. Okay, so when n is an odd power, that's when you get opposite directions. You're either going down to the left and up to the right, or you're going rising and falling the other direction. When n is an even number, when your degree is even, then you're going the same direction, either both of them going up or both of them going down. Okay, and so how you determine this is you look at the odd and even, and then you look at the leading coefficient. If the leading coefficient is positive, then you go down and up to the right. You go down to the left, up to the right. When the leading coefficient is negative, then you go up to the left and down to the right. When the leading coefficient is positive, you go up to the left and right both for an even function. And when the leading coefficient is negative, you go down to the left and right for an even degree. So the way I remember it is odd is opposite, and then positive means up to the right. And so if you can do that, you've got it down. All right, so just as an example, here we have f of x equals x to the fourth minus 4x squared. What is the degree of this polynomial? The degree is n equal 4. That's even. And then what is the leading coefficient? LC for leading coefficient. That's a sub 4. What is that? That's just the number in front of this. That's just a 1. I don't care about that. I care that that's positive. So what does that mean? That means your degree is even and your leading coefficient is positive. So even means they go the same direction. Positive leading coefficient means they go up to the right. And so they go up to the left and the right. And that's how I represent it. Okay, that's how I'm going to write it. There are some textbooks that will write it out and say as x approaches positive infinity, f of x approaches positive infinity to represent going up, and as x approaches negative infinity, in this case that's to the left, f of x approaches positive infinity. So you should be familiar with this terminology, but we don't really use it a whole lot. with us, but this is certainly done in, I know it's done in a lot of high school textbooks, this notation, and so you should be familiar with it anyway. Okay? So that's the idea of the leading coefficient. The next idea we need to talk about is the zeros of a polynomial. Zeros are when the function equals 0. So zeros have different names. You can call it a zero, you can call it a root, or you can call it a solution of the equation equal to 0. And so anytime you have a real root, it is an x-intercept. If you get imaginary roots, they're still legitimate roots, but they're not intercepts, right? So one of the powers of finding the zeros of your polynomial is that if it's a real root, that gives you an x-intercept of your graph, so that can help you sketch the graph. And taking the intercepts and your end behavior, you can actually get a pretty decent sketch of your polynomial function graph without much more information. And we're going to walk through that together. Okay? So with zeros, you then have to talk about multiplicity, because when we're talking about real zeros, they represent x-intercepts, and it's possible that you can have a multiplicity of more than one. And what that means is the root gets repeated. So like, for example, if you have 0 equals x squared minus 2x plus 1, that factors into x minus 1 squared. Well, it's a power of 2, which means we're supposed to have 2 roots, but in this case we only get one number. We get x equal 1. The root is x equal 1. There's only one of those, but it has a multiplicity of 2. It's what's known as a double root. And that means something about what happens at the x-axis when you hit that root. On your graph. When you have an even multiplicity, 2 is an even number, when you have an even multiplicity, the graph touches the x-axis and then turns around. It does not cross through the x-axis. If the 0 has odd multiplicity, which includes no multiplicity, a multiplicity of 1, right? That's not really multiplicity at all, then the graph crosses the x-axis. So you can tell whether or not it comes down, touches, and turns around, versus if it comes down and then goes through the x-axis. Okay? That's what we're talking about. So let's look at a picture of what's happening here. Find all the zeros of f of x and their multiplicities. Okay? So this guy, if we set this equal to 0, we need to look at this and we say, okay, this is one of these that probably needs to be factored by grouping if we're going to factor it. So we look at the first two terms, factor out an x squared, you're left with an x plus 2. Look at the next two terms, you factor out a negative 4, you're left with an x plus 2, right? The negative 4 comes out of the negative 8 and leaves a plus 2. And then the x plus 2 is one of your factors, and your other factor is x squared minus 4, but that's a difference of squares. So we can factor that and get x plus 2 and then another x plus 2, x minus 2, excuse me. And so that tells us we have x plus 2 squared and x minus 2. So this gives me an x equals negative 2 and this gives me an x equals positive 2, but the multiplicity of negative 2 is 2, where here the multiplicity is just 1, and sometimes we don't even call that a multiplicity, but that's the idea. Alright, and so what that means is that at negative 2, 0, we're just going to touch the x-axis, whereas at positive 2, 0, we're going to cross the x-axis. So, how does that help us with our graph? We take a look at the leading coefficient. It's positive, and the degree is 3. So what's your end behavior? It goes up to the right and down to the left. And if we take these two things along with these two intercepts, you'll see that you go down. Here's your negative 2, 0 intercept. You come up and touch, and then you turn back around. And then later, you go through 2, 0, and you cross through it. Okay? Now there's more information that's been used here. Here's a y-intercept, for example, that kind of stuff, and we're going to talk about that. But just to understand how the zeros work, that's how they work. This is what it looks like if you touch and turn. This is what it looks like if you cross. And obviously you can come from the other side to do either one of those. Okay? So why don't you guys try that? Here's a factored polynomial already. I've already done the hard part for you. I've done the algebra. I've factored it for you. Now just set this equal to 0. Solve for the zeros and state what the multiplicity is for each one, and then tell me what's going to happen on your graph. Okay, hit pause and try that here for a moment, and we'll come back and talk about it. Okay, so we have 3 factors. -4 is never equal to 0, so I don't have to worry about it. X plus a half is equal to 0, and that tells me x equals -1/2. It has a power of 2, and so that's the multiplicity. Multiplicity of 2. And what does that mean? That's even number, and so that means it touches and turns at the point -1/2, 0. Okay? X minus 5 equal to 0 tells me that x equals 5 is another intercept. It has a multiplicity of 3. And so what that means is that means it crosses. Okay? So the degree, what's the degree of this polynomial? 2 is the highest power here, 3 is the highest power here, 2 plus 3 because we're multiplying. 2 plus 3 is equal to 5. And we have a -4 out front, and so the leading coefficient is negative. So we go up to the left and down to the right. And so if we look at the graph, again, this is a little fancier maybe than we would be able to get, but we know it goes up to the left. Here it has a intercept of -1/2. It touches and turns, goes back up, comes back down eventually to pass through 0 at 5, x equal 5. And so 5, 0, it crosses even though it has a multiplicity of 3, so it kind of flattens out to cross. It didn't just go straight through. And again, we'll talk more about that as we get through this. Okay? But the fact that you understand what happens at these 2 points is what we're really focusing on right now. So how do I get a nice graph like that? What are the things we're going to use? We're going to use the leading coefficient test to get the end behavior. We're going to do all this stuff with multiplicities and zeros for the x-intercepts, okay, including the idea that if your multiplicity is greater than 1, 3, 5, 7, if it's greater than 1 and odd, then the graph flattens out near there. Okay, that's true for even too, but not as obviously. And then we find the y-intercept, and once we find the y-intercept, that gives us another point. And if you ever needed more points, you could use them, but just by plugging in. But that's kind of the process. All right, so let's walk through a problem like this together. Here is your function, f of x equals 2, x plus 2 all squared, x minus 3. Okay, and this is a 2, and this is a 1 power, and so you add them together, you get a degree of 3. The leading coefficient is 2, and so with an odd degree and a leading coefficient is positive, then it goes up to the right and down to the left. So now that we have the end behavior, we're going to go find the x-intercepts. How do you get the x-intercepts? You set f of x equal to 0. All right, what does that look like? Well, our function is 2 times x plus 2 squared, x minus 3. It's already been factored for you, so you get an x plus 2 equal to 0 and an x minus 3 equal to 0. So we have intercepts of -2 and +3. So now we need to find the multiplicities. The multiplicities come from the powers of the factors that give you the 0. So x equal -2 has a power of 2, multiplicity of 2. X equal 3 has a power of 1. 0 has a multiplicity of 1. Okay. So what does that mean? This means that we touch and turn around on the x-axis. This means that we cross straight through the x-axis, no flattening out because it's multiplicity of 1. Okay? So, when we take a look at this, X equals negative 2 is a 0 multiplicity 2. The graph touches the x-axis, flattens out a little bit, and turns around. All right. X equals 3 is a 0 of multiplicity 1. It crosses through the x-axis. Okay. So at x equal negative 2, you can see it comes up and turns around. At x equal 3, it goes straight through. So now we're going to get one more point. Let's find the x-intercept by plugging in x equals 0. If you plug in x equals 0, you get 2 times 0 plus 2 squared times 0 minus 3. So you get 2 times 4. 2 squared is 4 times negative 3. You get negative 24. Right? You're often going to get large numbers for these, and you just have to scale it appropriately. You do not have to tick off 24 points. You just label your points properly. Okay? So how I would like to see it from you, all right, how I would like to see it from you is that you notate your points. Here's the point negative 2, 0. Right? Here's the point 3, 0. And then here's the point 0, negative 24. You go down to the left. You come up and touch and turn at negative 2. You go down through your intercept and come back up to the 3, 0 point where you cross through. Okay, that's all the information I need. This does not have to be perfect. I don't have to have negative 10, negative 20 labeled. I don't need to see any of that. I need to see the points labeled here. Okay, obviously if you're doing it on my math lab, you have to follow the way that they do it. They allow you to plot points by typing the numbers in, so that'll be helpful. But when you're sketching these graphs, you certainly need to understand how to go through that process. Okay, so here's a problem for you to practice on. The function's already given in factored form again. So you find the end behavior, you find the x-intercepts with multiplicities, and then you find the y-intercept. And then I want you to plot those points, and I want you to give me a basic sketch for the graph. So hit pause at this point, try this problem, and see what you can do. Okay, so step 1, determine the end behavior. What is our degree? The degree is the highest power of x, which we get by adding the highest powers from each factor, x to the third, x to the second. 3 plus 2 is equal to 5, so that's odd. The leading coefficient is negative a half, which is less than 0. And so what does that mean for end behavior? Odd means they go opposite directions. Negative means it goes down to the right, and so that means it's going to be rising to the left. Our end behavior is going to look something like that. Step 2, find the x-intercepts. We set 0 equal to all these guys, and again, each is already factored out, and so the factors are pretty easy. X equal 1 and x equal negative 4. What is the multiplicity associated with this? Multiplicity here is equal to 3. Multiplicity here is equal to 2. What does that mean? That means here we cross and we actually flatten a little bit too. All right. And then here we touch and turn. All right, how about step 3? Step 3 is to plug in 0. So we get negative 1/2, 0 minus 1 cubed, 0 plus 4 squared. We get negative 1/2 times negative 1 times positive 16. 4 squared is 16. And so we get positive 8. So the y-intercept is 0, 8. Okay, so let's add a page here and write out a summary. Our function that we're graphing, negative 1/2 x minus 1 cubed x plus 4 squared, has end behavior that goes up to the left, down to the right, has intercepts of negative 4, 0 where we touch, and positive 1, 0 where we cross but we go flat a little bit, and then of course a y-intercept of 0, 8. So what would that look like? Here's our negative 4, 0 over here. Here's our positive 1, 0 right there. Here's our 8 y-intercept, 0, 8. We're supposed to come down and then go down, so we go down to here. We touch at negative 4. We go up. I don't know that we max out before or after 8, it doesn't really matter, but it's eventually I got to come back down, and then I'm going to go straight down. But because of the power of 3, I know that this actually comes down and flattens out a tiny bit and then goes on. Okay, and I sketched it here for you on Desmos just to kind of show you what it would look like a little bit prettier. If you did it on your calculator, it probably looks similar. Again, the way that I drew it, it was not quite as correct as far as the maximum number goes. That requires calculus to find that little hump there, that local maximum happens at -2. You don't have to worry about that. I'm perfectly happy with this graph, as ugly as it looks. It's got all the key stuff in there. It's got the 2 intercepts, it's got the things that happen at those intercepts correctly, and it's got the y-intercept in it, and it's got the correct end behavior. I'm totally happy with this picture right here. All right, that's all I'm looking for. So hopefully that helps. If you have any questions, as always, shoot me an email, and we'll make a plan. Okay, thanks.